So alpha is same for competitive inhibitor, uncompetitive inhibitor and non-competitive inhibitor. That will be equal to 1 plus your inhibitor concentration divided by your inhibition constant Ki. Yeah? So what we have? So we know that our initial velocity or R0 will be equal to K catalyst multiplied by enzyme substrate complex concentration. So we need to find this value, enzyme substrate concentration. So let's do that. So you have R catalyst multiplied by ES. So all looks fine. So how to do this value? So you have E plus EI that give rise to ES value. Okay, let's replace this one, this E and I. So that's E. So E total equal to E plus. So we know that the enzyme substrate inhibitor complex will be equal to, if we come back to equation here, so Ka is equal to, just look at this part of the expression. So from this we can get the concentration of EI. That will be equal to enzyme concentration multiplied by inhibitor concentration divided by Ki plus enzyme substrate complex multiplied by alpha. So this is okay. So now we can take this one, take E common factor outside, so that will be equal to 1 plus concentration of I divided by Ki plus Es alpha. So now this is equal to E alpha plus Es alpha. So let's take the alpha common factor outside. Alpha will be equal to E plus Es. So what is this? This is nothing but equal to E total. So E total is equal to alpha multiplied by E plus E enzyme substrate complex. Yeah. So let's give this some number. Let's call equation 3. Okay, so far good. So E total is equal to alpha multiplied by E plus enzyme substrate complex. So we have to get R0 value, or initial velocity, which is K catalyst multiplied by enzyme substrate complex. So what can we do this? So we can rearrange equation 3. That's the easiest way to deal with this. E plus Es is equal to E total divided by alpha. E total divided by alpha. And then we can also replace E with the enzyme substrate complex. So we know that association constant. Still we need to use this value Km. So Km is nothing but enzyme concentration multiplied by your substrate concentration divided by enzyme substrate complex concentration. So therefore concentration of E will be equal to Km multiplied by Es divided by your substrate concentration. So let's put 4. Let's call this as equation 4. So substitute this E value in this above expression. So that will be Km enzyme substrate complex divided by substrate concentration plus Es, that's equal to E total divided by alpha. Okay, I think we are almost there. So let's take enzyme substrate complex as a common factor. So that will give 1 plus Km divided by S. That will be equal to E total divided by alpha. Okay. So from here we know what is alpha. From here we can get enzyme substrate complex. So therefore enzyme concentration of enzyme substrate complex, that will be equal to E total divided by 1 plus, or maybe just divided by alpha. That's what we have here, E total by alpha, and then this term should come to denominator, so that will be equal to 1 plus Km by S. So this is good so far. So, and we know that initial velocity is equal to K catalyst multiplied by enzyme substrate complex. So let's call this as equation, okay, let's call this equation 5, let's call this as equation 6. So substitute equation 5 in 6. So at the end of the day we are calculating enzyme substrate complex, and we have to, and we don't want to see the parameter like enzyme inhibitor concentration or enzyme substrate inhibitor complex concentration. This is something we cannot measure, so we have to eliminate these parameters appearing in the final expression. So R0 is equal to K catalyst multiplied by E total divided by alpha 1 plus Km divided by S. So so this almost look like our Michaelis-Menten kinetics, but still we have to do something. So R0 is equal to K cat multiplied by E total, that's equal to mu max divided by alpha. Then just expand that expression, S plus Km divided by S. So your S will go to the numerator. R0 will be equal to mu max S divided by alpha S plus, no, this is alpha S by S plus Km, no, this is not correct. R0 will be equal to mu max multiplied by S divided by alpha S plus Km. So if you expand it, R0 will be equal to mu max multiplied by your substrate concentration alpha S plus alpha Km. Okay, so this is good. So that's the kinetic expression for or if you are going to deal with a non-competitive inhibitor. So if we have a non-competitive inhibitor, then our initial velocity as a function of substrate concentration can be expressed using this expression. R0 is equal to mu max multiplied by S divided by alpha S and alpha Km. So we can, in order to get some more understanding, we can do something. So what I am going to do is I am going to multiply and divide divide numerator and denominator by alpha. So alpha is something related to your inhibition constant. Okay, so if your alpha is 1, which means inhibitor has no effect, and then R0 will be equal to mu max S divided by S plus Km. So this is for a pure enzymatic reaction. This is nothing but your Michaelis-Menten expression. So if you have some inhibitor acting on the or involved in the enzymatic reaction, then alpha will not be equal to 1. So that's the message you should that you should take home. Yeah. So you have R0 is equal to mu max multiplied by, yes, this is for Michaelis-Menten, and that's this expression. Let's call it equation number 7. So that's the expression that relates your initial velocity as a function of substrate when we have a non-competitive inhibitor. Yeah. Okay. So let's divide numerator and the denominator of equation 7 by alpha. So R0 will be equal to mu max S by alpha divided by alpha S by alpha plus alpha Km by alpha. So this way alpha get cancelled, and then you will end up with R0 is equal to mu max by alpha multiplied by substrate divided by S plus Km. So this expression says something to us. What it says is like, if we have a non-competitive inhibitor, then your Km will not be affected, but your mu max, your maximum initial velocity will change, and that change will be associated with some factor which is given by alpha. Yeah? So your mu max will decrease by some amount, so it will be like mu max divided by alpha. So but it will, the whole idea is like, if you see here, Km is not multiplied by any inhibition factor like alpha, but your mu max decreases by some amount, so it will be equal to 1 by alpha. Yeah? So if you really do some experiment, let's say we have a substrate concentration, initial velocity. So if this is pure enzymatic reaction, no inhibitor, or in other words, so it will look like that. But when we have a non-competitive inhibitor, maybe this is not a great graph, I will try to redraw it. Substrate versus mu. So let's say you have some graph like that. So this is no inhibitor, and then when you have a non-competitive inhibitor, you will get something like that. So this is your mu max for pure enzymatic reaction, and that's the mu max. Your mu max will be equal to mu max by alpha when you are going to deal with non-competitive inhibitor. You're dealing with the non-competitive inhibitor, but one thing that you have to remember is this mu max by 2, and so let's draw a line here, and then this mu max alpha by 2, that somewhere is around here. So that's the mu max by alpha by 2. So if you draw a line here, okay, this graph is not great, so let me draw something like that. So your Km value will not change. So if you are performing a pure enzymatic reaction without an inhibitor, your mu max will be equal to mu max, and then your Km will be equal to Km. Or in other words, your substrate, your initial velocity will be exactly equal to mu max by 2 when your substrate concentration is equal to Km. So this is for no inhibitor. But when you have a non-competitive inhibitor, your maximum initial velocity will be equal to mu max by alpha, and then your maximum your initial velocity will be equal to mu max by alpha by 2, which is exactly half of this value when S is equal to Km. So your Km will not be altered, so Km will not change, but your mu max will change by a factor of alpha, 1 by alpha to be precise. So this is for the non-competitive inhibition. So you have to remember, so when we talked about competitive inhibitor, competitive inhibitor, let me check one time, I don't want to do any mistake. So when we talked about competitive inhibitor, your mu max will not change, but your inhibitor will alter the Km value. Km will change. When we deal with uncompetitive inhibitor, mu max and Km both will change. So your inhibitor will alter the maximum initial velocity, and it will also decrease or change the Km value. So both will change. And if we are going to deal with a non-competitive inhibitor, your mu max will change, but Km will not change. So Km will remain same. So when we have uncompetitive inhibitor, Km will increase. When you have competitive inhibitor, again Km will change, or in other words, it will increase. Okay, so these are the effects of the three different type of inhibitors. So we have competitive, uncompetitive, and non-competitive inhibitor. So next we need to learn how to get these kinetic parameters like say mu m and Km for pure enzymatic reaction. So for this we need to use the Michaelis-Menten kinetics. And then for a competitive inhibitor, how to get these constants mu m, Km, alpha, Ki. So how to get this? For this we need to use this rate expression mu multiplied by S divided by alpha Km plus S. And then for a uncompetitive inhibitor, how to get these parameters mu m, Km, alpha, Ki, and then we need to use this expression, which is the rate expression for uncompetitive inhibition kinetics, mu m S divided by Km, alpha multiplied by S. And then again for non-competitive inhibitor, how to do that? We need to calculate again mu m, Km, alpha, Ki, and then obviously we need to use this expression which we derived just now, Ks alpha Km plus alpha substrate concentration. So these are the rate expressions. So how to get that? So for that we need to use the Lineweaver-Burk plot. So that's something, it's not a big deal, it's really easy. So before that we will try to write it. Let's write the Michaelis-Menten expression. R0 is equal to mu m S Km plus S. I'm going to replace this R0 with initial velocity mu. That's the most conventional notation used in many textbooks. Mu is equal to mu m S divided by Km plus S. So just to take the inverse of this expression, so 1 by mu, that's equal to Km plus S divided by mu m S. So we can expand this expression, 1 by mu, that's equal to Km divided by mu m S plus S divided by mu m S. So S get cancelled, so you will get 1 by mu, that's equal to Km divided by mu m multiplied by S plus 1 by mu m. So this is like a concentration. Yeah? So to get your mu m, mu suffix m, and or this constant, equilibrium constant Km, all you need to do is you need to plot 1 by mu on the y-axis, 1 by s on the x-axis. If you plot these values, you will get some slope that will be equal to Km by mu m, and then you will get some intercept that will be equal to 1 divided by mu m. So intercept will be equal to 1 by mu m. And then your slope will be equal to Km by mu m. So once you know your mu m value, you can calculate Km will be equal to slope multiplied by mu m. So you have to first calculate maximum initial velocity and then you substitute that here. So Km will be equal to slope multiplied by mu m. Hope you are okay with this. So this is so whatever the plot we have here, 1 divided by mu, 1 by substrate. Sometimes people call this as a double reciprocal plot. Double reciprocal, and that's because we have one reciprocal here, 1 by mu on the y-axis, and another one reciprocal here, 1 divided by your substrate concentration on the x-axis. Yeah, so what's happening? So just follow the red ink. So you have 1 divided by substrate concentration here and another reciprocal here on the y-axis. So that's why we call this as a double reciprocal plot. So that's how we get the kinetic constants mu m and Km for the pure enzymatic reaction. So in the next lecture I will show you how to get the kinetic constants as in this type of expression when we are going to deal with a competitive inhibitor, uncompetitive inhibitor and non-competitive inhibitor. So thanks for listening.